Hello, everyone. I just finished my book of proof stream, and now I'm going to be switching gears over to algebra and trigonometry. Okay, so let's start a new page. Okay, so we're doing 1.3. Let me just test to make sure everything is properly connected and that I'm broadcasting. Okay, I think so. Perfect. I can hear myself. All right, good. So just checking off my headphones and perfect. So what I'm going to do now is I'm going to do a reading of the chapter and then we are going to do the equations. Now, a couple of real quick things. This is the book. It's called The Algebra and Trigonometry. Download the book. It's in the video description. It's borrowed of the OpenStax initiative. And also, you can get a physical copy. The physical copy is really nice. I don't get anything for it. I'm just saying that support the authors. It's a great book. Anyway, myself, I have taken and passed this class before, but I am not a teacher. I am a professional landscaper / handyman. I go to Westchester University for computer science and pure math, a double bachelor, and I currently have an associate in computer science from Delaware County Community College. So for me, this is like a long-term project. I am happy with my work, but I also love learning new things. I'm also a figure skating coach. I teach twice a week, and I just came back from coaching. Anyway, let's start with 1.3. Radicals and rational expressions. A hardware store sells 16-foot ladders and 24-foot ladders. A window is located 12 feet above the ground. A ladder needs to be purchased that will reach the window from a point on the ground 5 feet from the building. To find out the length of the ladder we need, we can draw a triangle using the Pythagorean theorem. Okay, so we have, let's draw a diagram. It's always good to draw diagrams. So this is going to be here. A window is located 12 feet. So we're going to have a window here. So this is going to be 12 feet. All right, then we have, let's see here. Next, we're going to say a ladder needs to be purchased that will reach the window from a point on the ground 5 feet from the building. So basically what it's saying is that the angle has to be, so this is the building, and this is going to be 5 feet here, which, in other words, we're going to prop the ladder 5 feet away, the legs of the ladder, and we want to know what the difference is. So this is using the Pythagorean theorem, so which is, here we go. And that is a squared plus b squared is equal to c squared. All right. So let's do that. And we're gonna say 5 squared plus 12 squared is equal to c squared, which is 169. And then we're just gonna square root because it's a c squared, so c squared is equal to 169. Square root. Now, if you don't remember off the top of your head, that's 13. And yeah, that's good. So this is gonna be 13 feet. So if you think about it now, they sell 16-foot ladders and 24-foot ladders. As long as our ladder is 13 feet or longer, then it'll be fine. So I'm guessing we'll end up getting the 16-foot ladder here. All right. So, by the way, this is all on page 31. I'm doing this because I'm just going to kind of go over all of the work that they give us, because it's not that I can't do it on my own. I certainly can, but I want to be able to go and, if there's any little tricks and tips that I may have missed over my time, that's when I want to, like, go over this stuff. I want all this math knowledge to be at my fingertips, even the stuff that I've passed. Anyway, so because it's hard to know what you've forgotten until you need it, and then it just becomes annoying when you're trying to, like, does it go this way or that way? You got to polish those skills. So that's what I'm doing. Now, we need to, let's see here. Okay, now, evaluating square roots. When a square root number is squared, the result is 0. Yes. Okay, so I'm not like reading word for word the whole thing because that would just like take up a lot of time. You should, though, if you don't know what any of this is. But I have to get through another 7 pages, and I want to do it relatively briskly. So anything that I can, because I need all the knowledge we're going to need. Any tips and tricks they want to throw at us. And basically, yeah, like for instance, this right here. So yeah, this is the radical. So we're going to write what they have here, 25. This is radical. I'm copying from the book. Radical. This is radicand. So if someone says, what is the radicand of root 25? It's the 25. And the radical is the square root sign. And this right here is the radical expression. See, I didn't know that radicand thing. If someone they wanted to mess with me, like, hey, you know, on a test or whatever, you know, I'll be taking calculus. Not that they would. I mean, but they say, what is the radicand of root 25? Like, what are you even asking me, right? This is why you got to go back and review this material. All right. The principal square root. The principal square root of a is a non-negative number that when multiplied by itself equals a. It is written as a radical expression with a symbol called a radical over the term of the radicand. Okay. So, yeah, essentially what... So, does a root... Okay. Here's the thing. This is another thing, important thing, is that 25 plus minus 5. No. It is always positive. We're not doing... You can't have negative 25. So, negative 25 is equal to root 5i. I could be wrong, but because I haven't done imaginary numbers in any significant way. But, I mean, I'll get to them eventually. As I understand it, though, here we go. Root I is equal to negative 1. So, no, sorry. That's incorrect. I think it goes like this. I is equal to root negative 1. Believe that's how you properly say that. So that's the imaginary number set. And it has to do with, you would rotate the polar coordinates. So, yeah, it's complicated, but it's not that complicated, I guess. I don't know. I'm speaking from ignorance here. That's all I got to say. Don't take anything I say too seriously, and please don't quote me to your professors. All right, their life is hard enough as it is. Okay. Okay, now we have... Let's go through a couple of evaluations here. Mostly, I just want to look for any tips and tricks they want to give us. So, just go over... They have the solutions on here. We're still on 32. Root 100, which is 10. Yeah, because 10 times 10 equals 100. All right, then we're going to say B. I want to look at some of these interesting ones here. I'm not looking at the answers. I'm just doing them on my own, which is going to be root 4, which is equal to 2. See if I got that correct. Yes. Okay, good. You work from the inner part to the outer part. C is going to be root 25 plus 144. We do with the inner part, which is going to be root 169, which is equal to 13. All right. Yes. And D. Okay. Root 49 minus root 81. So, in terms of PEMDAS, where is... I guess PEMDAS... powers, or yes. So if we say PEMDAS, so we have parenthesis, exponents, say x to the a, yeah, multiplication, division, addition, and subtraction. Okay? And since I did A's and B's, I'm just going to do this. All right. I'm going to say A to the B. Now, here's how I'm going to prove why it's part of the exponents. Why the root is part, well, it kind of is because it's the inverse of it. But also, you can just do this. Okay, A to the B, or if it's the negative B. So the negative makes it a square root. Well, no. So yeah, it is, yeah, like if you take 16, I'm right here. Let's do this. Yeah, 16 to the negative 2. It would be 1/16, which would be 1. Maybe I'm not. See, this is why I study this stuff, because I am saying things that are not necessarily correct, and now I have to see if what I'm saying makes any sense. No, that wouldn't work. That would be 1/4. So negative is not the same thing. It's not a square root, but I would expect it to be in the exponents. So D would be 7 minus 9, which is equal to negative 2. All right. Yep. Okay. So let's see here. Okay, now. Okay, so anyway, we have using the product rule to simplify. This is what I wanted to know. Yes. To simplify a square root, we rewrite it in such that there are no perfect squares in the radicand. There are several properties of square roots that allow us to simplify complicated radical expressions. Yes. See, I'm not good at this part. These kind of tricks is what I want. The first rule is that we look at the product rule for simplifying square roots, which allows us to separate the square root of a product of two numbers into the product of two separate rational expressions. So, let's go to the next page here. Okay, and all right, so here we go. Oh, why did I paint it black? Oh, this is gonna be cool. It doesn't work that way, does it? No, it probably does. If I do a black screen, what would happen? I just want to try this for a second. Oh, cool! I got a blackboard. That's neat. But no, I like it white. It's easier to read. But yeah, that's definitely cool. I should maybe play around with that. Switching it back. Okay. All right. Okay. We have. Okay, so yeah, for example, root 15. Now, getting root 15 is kind of hard. So it's just like at the top of your head, hard, meaning that you could always just use a calculator, but we could say root 3 times root 5, because you could do that. These can combine into 3 times 5, which is equal to root 15. You can separate it like that, and that's the product rule. So yeah, so I actually knew this. I just forgot it was called the product rule. I'm terrible. I'm like, yeah, calculus 2. I remember doing all this, pulling things out and putting them back in. And I'm like, I don't even know what it's called. Anyway, I did wing that over the summer. But it was a great teacher. Speaking of that, so my teacher, his kids one time, this was over Zoom, they were like 10 or 11 or something, and they come to him with a calculus question while he's teaching the class. I mean, it was something to that effect. I don't remember exactly, or he mentioned that his kids are doing calculus. But long story short, at first I was kind of like shocked, thinking, wow, you have these, must be really smart, 10, 11-year-olds doing calculus. But then I thought about it, I was like, well, it's no different than like when you're seeing a figure skater that's like 10 or 11 and they're working on their double jumps. It's like, yeah, I mean, it might seem early, but then if you get an early start, it's just you'll learn the techniques, and it's just like anything else. You polish out your technique. in math, there seems to be this, how do I describe this? Like, people look at it and they think, oh no, I'm not a math person. I could never get this. It's like, sure you could. Why not? You know, if you could learn how to run and jump and whatnot, you just take the time and you could learn it. It doesn't take, I mean, obviously if someone has exceptional ability, it makes it easier perhaps, but I'm not especially capable or competent. I mean, as you can see, of the 6 books that I'm going to be doing on this channel, 3 of which are classes that currently I'm holding an F or a W in. Probably an F at this point, but I don't care. For me, it's all about the knowledge, and I dropped them or got Fs because I had to focus on my landscaping business. So yeah, that's fine with me. I'll retake them. The important thing is getting the work done. Anyway, back to this. In case you don't know, I do go on unrelated tangents every now and then, and that's just the way I am. I always have been. Right, we are in 1.3. We covered the product rule, and using the product rule, let's see if we can do this. We're going to simplify root 300. Okay, so I'm thinking we can go 3 times root 10. Hold on a minute. Times 100. Yeah. And that's going to be 10 root 3. Voila. Yeah, that's it. And you can just take a calculator and go root 300. What does that give you? 17.32 and change. And then you can go 10 times root 3. Yeah, it's exactly the same thing. So now here's the trick. If you have base like 100, or like for instance, let me think about this here, another one. Yeah, like if you go by hundreds at least, it's very simple. Just you pull out, and not just even the hundreds. For instance, you have like, let me think of a number here. 75, right? Root 75. It's same thing. Just top of my head. So we're gonna say root 3 times root 25, which is equal to 5 root 3. So it's like that. It's really not that bad if you can just kind of like pull numbers apart. And if you can't, that's okay. You have to manipulate numbers. You gotta put pen to paper in order to get better at math. You can't just like listen to a ton of streams. It's just the retention's just not there. I've listened to so many different things that, you know, I retain bits and pieces of them, but nothing working knowledge unless I actually practice it. You have to live it. So let's try this. Root of root 81, simple 3. So basically root of 81 is 9, root of 9 is 3. So that's a very simple one. Okay. And then we're going to say 25 minus 9. Okay, so here we want to simple both of them. Here's the thing though. We can split them and then, okay, let's try that. Let's roll with this. So there's 2 ways to do it. If we were to do the addition inside it, and I want to make sure this gives us the right answer because it might not. If we go, let's see here, this is going to be root 16, right? And 16 is going to be 4 times 4, which is equal to 4, yeah? All right, so that's right. Now, what if we did this? I just want to try that. So yeah, here's the thing. You can't not equal to doing this. Root 25 minus root 9, which would equal to 5 minus 3, which is equal to 2, right? So it's not the same thing. You have to do the inner part. It's important. Okay, so that's going pretty well. Let's try D. And again, these I'm just not going to order them because some of these I just threw out that were top of my head. So root 121. All right, so the first one's going to be 6 plus 11. 17. So 11 times 11 is 121. And that's just like, you know, like some of the numbers, you work with enough numbers that some just, you know, you kind of know what they are, what the root is, what the square root of it is, just top of your head. But these are very, very small numbers. Like just very tiny numbers if you think about it. I mean, it's all relative, of course, what you're working with, but in terms of what a number actually is, how big a number can get, even a billion, billion, trillion is still almost, it's roughly what it is as the distance between a 0 and 1. Because although it's a huge number, you can go a billion times billion times billion times billion times trillion to the power of quadrillion to the power of quintillion. So, you can grow these numbers so mind-bogglingly huge that it's just, it doesn't matter. Even those numbers, they're still, I only, threw out those numbers over the course of a few seconds. What if you spent the rest of your life describing powers of numbers and so forth? Or, or you got a googolplex to the power of a googolplex to the power of a googolplex. So yeah, it's just like that. Anyway, let's continue. And a googol is 1 followed by 100 zeros, in case you don't know. And a googolplex, I believe that's a googol times a googol. Let me look it up. Just since I brought it up, I want to confirm what it is. Okay. Oh, here we go. A googol, officially known this is too long, as a 10 duo trillion, as officially known as 10 duo trigentillion or 10,000 sextillion is 1 with 100 zeros after it. That's a googol. That's yeah. Or 1 times 10 to the power of 100. And let's see here. A googolplex, okay, is basically, which is 1 followed by a googol of zeros. So basically a googolplex to the power of 10 to the power of 100. Yeah, crazy numbers. And, you can keep growing that. So as I was saying, what is large, what is small, it's all relative, because with infinity, it's just, I mean, there are ways of categorizing the sizes of things, but yeah, we'll get to that later. Let's just continue. I don't want to take this too long. Okay, so we use the product rule. Yeah. So let's see here. Factor a perfect square from radicand. So right here, this is a perfect square. Okay. And like 25, I believe. Here. Let me see here. Okay, so the perfect square list is 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121. They're all perfect squares and just keeps going. Yeah. If you take a positive integer, positive whole number, and you multiply it by itself, you get a perfect square. So like 81 is a perfect square. 169, 13 times 13 is a perfect square. Okay, we're having fun here, right? Right, let's go to the next page. Okay. So we did that. Now this one right here. 81, and we're going to say a to the 4th power, b to the 4th power times 2a. Okay, So let's see here. We can pull out the perfect square, which is going to be root 81. And then is there anything else we can pull out of here? Okay. Right. So when you have a whole number, I'm sorry, when you have a variable that is to the power of a perfect square. In this case, we have a to the 4th power. That is still a perfect square. I'm going to show you why. We're going to say times root 2a. And that's when we square root it, we have 9. And then it's going to be a squared, b squared, times root 2a. All right. All right, good. And here we go. So let's try, let's see here. Okay, so far so good. Using the product rule to simplify the product of multiple squares. Okay, so here we go. Let's try this. We're going to say 12 times root 3, which is equal to, we can just merge them. And we're going to say 12 times 3. Because if you multiply on the outside, you can pop it in. And you could also pull it out. But if you're pulling a number out of a square root, that number, whatever you're pulling out, has to be square rooted. For instance, if your number results in a whole number and you can put a 4 out of it, let's say 48, right? So you can pull the 48 out, you'll leave 12 in there, and the 4 becomes you're pulling out a square root of 4 because you're still in the square root. Then you square out the 4, you get a 2, you pull the 2 out. So that's how you do it. In this case, you do kind of the opposite. You can merge the 2 and you get root 36, which is a perfect square because that's 6. Nice. All right. And then we're going to simplify this. Root 50x, and then we got times root 2x, and then we're going to say, assuming x is greater than 0. Okay, so here what we have is, we're going to merge and see what we get inside there. Oh, it's 10x. So this is going to be 10x. That's the answer. So notice that we get 2 perfect squares when we merge it. So basically we get root 100 x squared, which is equal to 10x. All right. Yeah, again, introductory stuff like this to give us really simple, obvious stuff. All right. Here we go. Using the quotient rule. All right, let's just, the quotient rule goes like this. If you have a square root, hang on a minute, something's not right. My battery's running low. Hold that thought. I'm going to see what's going on. How did I lose power? Give me 1 second. All right, hold that thought. I'm going to get the power up. Okay, I think we're back in business. Sorry about any flashing that you may have seen. So let me just see here. Yeah, I think we're doing okay. I want to check on the stream, make sure that the stream wasn't disrupted. Sorry about that. Okay, yeah, we're still running, so that's good. Okay, now, so the quotient rule, as I was saying, so you can do this, A over B. So yeah, it's the same kind of a thing. This is division, basically. So yeah, we were able to pull that out into two separate fractions. That's good. Now, let's just do this. Root 5 over root 36, which is going to be root 5 over 6. All right. Now we're going to simplify. Here we go here. Good. And one more thing, I want to check on the audio of the stream. Make sure that all the sound is coming through properly. 1 second here. Yep, okay. The stream seems to be up and running good. Right, let's continue. So we have, I'm going to do this, root 2x squared over 9y to the 4th power. Let's use the quotient rule. We're going to spread this to, I'm going to do this in several steps so it doesn't get confusing. I'm going to say x root 2 because we can pull out just a square root of the x, so that's fine. And then we're going to say 3y squared. All right, yeah. All right, good. And here we go. Good. All right, so now let's continue. Let me just see here. I want to make sure not to see here. Okay, so let's try this. Okay, we're going to go to this. We're going to add 5 root 12. Let's start a new page. I'm going to say 5 root 12 plus 2 root 3. Okay? And this is the example. We're doing 6. Okay, so now what we're going to do is this. 5 times root 4 times root 3, which is equal to, wait a minute, plus 2 root 3, which is equal to 5 times 2 times root 3 plus 2 root 3, which is equal to 10 root 3 plus 2 root 3, which is equal to 12 root 3. Okay, yep, all right. Good, and good. Now, there are triad sections. I'm kind of skipping those for now. We'll be seeing them in the equations. I want to get to the actual questions. Here we go. Okay, well, this right here is an interesting one. Let's try this, 20. So we want the common denominator, right? So let's try by, we need in the fraction, so root 8, a to the third power, b to the fourth power, and c. We need those. So what we can do is this, we're going to say 20. But what we can do is we can say root, and we're going to say 72 is going to be 9 times, actually we're going to say 9 times 8, okay? And then we're going to say a to the fourth power, b to the fourth, and c, minus 14, 8, root 8, a to the third power, b to the fourth power, and c. So now, check this out. We're going to take the 9, we're going to pull out the 9, and that's going to be a 3. Because root 9 is equal to 3. So now we're going to multiply 20 times 3, and we're going to have that change here. That's it. Okay, now we have Emmett. Okay, and now that's going to be 36. Yep, 30, wait a minute here. 40, sorry, not 36, 46. Also, we're going to pull the b out. B squared, we can do that. And then c. That's good. Let me see if there's anything else you can do with this. Yes, we can also pull the 8 out. So, but not exactly. We're going to say 46 times, I'm going to show you what we're going to do here. So we are going to pull this out. It gives us 2 because root 4 is 2. So 46 times 2 is going to be 92 b squared times root 2 a to the third power c. That's what I'm getting. They did something a little different. I want to see what they did here. Okay, hang on. Oh, okay, no, that's fine. You can technically split up the a. So what you can do is this. You can also still do this. (92) b squared. So what happened is, what we did here was we went 92 b squared. Okay, what we did here was we went 92 b squared, then we took the root. We're going to say 2 times a squared times a times c. So the a squared gets pulled out. Root of a squared is equal to a, or plus minus a. Actually, hold on a minute. No, that's wrong. So that's powers. So it has to be positive a. It can't be negative. But what if a was negative 4? What if we square rooted negative 4, right? So the condition here is that, so for instance, let's say it was, because we're pulling out a square, it can be positive or negative. So the result is always going to be the positive a. So when we pull this out, and then, for example, if a was negative 4, because we can't square root negative 16, it would be negative, it would be 4i, right? So in that case, what happens instead is we put it out as absolute value. So this is equal to the absolute value bars. So no matter what you do, you're always going to get with a positive a as the result. So that means that the result will always be positive because it is being squared inside the square root. But the square and the square root cancel, and that gives us a positive result because the base of it, the first action is the square, and the square will always result in a positive number. Okay, so yeah, that was a fun one. I really like this stuff. Okay, so let's see where we're at. Okay, so we have good rationalizing denominators. Okay, that's, I know what that is. Here we go. Okay, we're gonna do this. 2 root 3 over 3 root 10. What is their simplest forms? Okay, so so in terms of the simplest form, that means we have to get rid of the square root at the bottom. And the way we're going to do that, we're going to go like this. So if you have a, now, to be clear, if someone says that, you have to do this or that equation, and then just to simplify afterwards, solve, and then simplify. If you leave it with the root, some teachers are okay with it, they don't care. But some, they will require you to get rid of the square root in the base. And the way to do that is you multiply it, both numerator and denominator, by the square root. Now, you can raise any equation to whatever power you want, as long as you apply it equally. You can increase both the top and bottom by 2, by 10, by 1,000, as long as you apply it equally, because the relationship in a fraction remains the same. So just as 100 over 200 is the same as 1 over 2, because you say, well, it's pretty obvious. You get 1 for 1. You, in other words, for every item you get, there is, so for instance, like this. For every item that you take, you have to bring back 2. Okay, so then in this case, you took one item, you brought back 2. So you brought back twice as much. And if you take 100 items and you bring back 200, you're still bringing back twice as much. So you see how that works? So now, so this is totally fine. So when we do this, we're going to say 2 root 30 times 3 times 10, which is equal to 2 root 30 over 30. Okay? And then what we have is we just have to simplify one more time, which is 30 over 15. Voila. Okay. So yeah, that's pretty straightforward. It looks weird, I know, but trust me, it works. If you are in doubt, just run the calculation and see that you'll get the same result. In other words, you run your calculator, multiply out the numerator and then the denominator, and then do the division, and then do the same thing with the result to get the same result. And if you want to know, like on a calculator, how to get, if your calculator is spitting out like a root fraction, so just whatever equation that you're applying, you want to enter a, for instance, if you went in your calculator, you went root 8, right? And it says to you it's going to be 2 root 2. You're like, well, what is that in decimals? Here's what you do. You go root 8, period. And then it'll spit out the decimal for you, which I'll do right now. It's probably going to be something like 2.8. Yeah, it's going to be about 2.8. Let's see here. Let me do this. Yeah, it's 2.8284 and so forth. Right. 2.82. Okay. Good. All right. So that's that. So let's continue. Okay, we have, let's see here, rationalizing. Okay, this is an interesting one. Let's go to a new page. So we have 4 over 1 plus root 5. So what we want to do then is we want to, let's see here. This is how they're going to tell us to solve it. Begin by finding the conjugate of the denominator by writing the denominator and changing the sign. So this, let's see here, a plus root b is hang on a minute, that's probably, so you change the sign. Just change the sign. Okay? Alright, here we go. So let's do that. Top and bottom, that rule remains. So the way you do it, remember, you have to spread it out. So 4 times 1 is 4. Negative root 5 is going to be 4 root 5. And then we're going to say bottom is 1 times 1 is 1. And we're going to say 1 times root 5 is root 5. Let's see here, and then wait a minute here. 1 times 1 is 1, yes. Times root 5 is root 5. Did I just write 1? Yes. And then, yeah, we're going to say minus root 5. Negative root 5 times 1 is negative root 5. And then finally, root 5 times negative root 5 is 5. 5. Oh, negative 5, sorry. If there's one negative sign in there, the whole thing becomes negative. In other words, the negative 5 and negative root 5 gives us 5, but the negative carries over from the first one. So these two cancel. This is going to be 4 minus 4 root 5 over 1 minus 5, which is equal to 4 minus 4 root 5 over negative 4, which is equal to, we're going to take the sign, we're going to move it to the front, 4 plus 4 root 5 over 4, and then we're going to simplify it, negative 1 plus 1, and we don't want to do 1 over 5, we're just going to say root 5 over 1, which is equal to minus 1 plus, wait a minute. Because I'm breaking up the fraction, that negative transfers back in on the root 5. Minus 1 minus root 5. I think that's the correct answer. No, actually it's still positive. This is positive. Let me see what I did wrong here. Okay, I sped through it somewhere and I made a mistake. I want to catch my mistake here. Let's see here. Okay, that's correct. Okay, so what I didn't need to do is I didn't need to pull out the negative. Let me fix this. This was an unnecessary step if I was to get rid of the fraction. So really, I should have kept simplifying it before doing all that. So here's what I'm going to do. Let me try again. Let's continue where I'm going to just change the signs one more time. I'm going to come back to all this in a minute. I'm going to add all the signs here. So, and by the way, it's fine to make mistakes. There's nothing wrong with that as long as you understand the process and you learn from it. That's what really matters. So we have 4, 4, and 4. So we're going to say dot, 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 and make those ones. So we get negative root 5 over 1 over this way, over 1, negative. And now at this point, this negative turns the negative 5 into a positive, and it's going to be negative 1 plus root 5. Yep. So that's good. Yeah. That was it. I just kind of blew through that. You can do that, pulling out the negative early, which you can do that, but the thing is I did it wrong. Anyway, this is the correct way to do it. Meaning that I just made a sign error. Nothing significant, but I mean, yes, it is significant in the sense that it's still wrong, but it's not like a misunderstanding of process. Okay, so all right, let's go to the next page. We have, this is using rational roots. Let me get a drink real quick here. I don't want to sound too gravelly. All right. Although square roots are the most common rational roots, we can also find cube roots, fourth roots, fifth roots, and more. Just as the square root function is the inverse of the squaring function, these roots are the inverse of their respective power functions. So, in other words, let's see here. So if we have, so like just as, we'll do examples in a minute. We're going to look at their examples instead. Understanding the nth roots. Suppose we know that a to the third power is equal to 8. We want to find the number raised to the third power to 8, since 2 to the third power is equal to 8. We say that 2 is the cube root of 8. The nth power of a number, so in other words, 2 to the third power is equal to 8. 2 is the cube root of 8. All right? The nth power of a number is that when raised to the nth power, it gives a. So essentially, we want the number. So let's say the nth power. What is the nth power? So let's say 10 to the n equals to 100. Well, then n is equal to 2 because 10 squared gives us 100. Okay? Yeah. The principal n root of an a is the number with the same sign as a that when raised to the nth power equals a. The principal nth root is written as wait a minute. I'm gonna write it a little better. N over a. Okay? Where n is the positive integer greater than or equal to 2, and the radical expression n is called index of the radical. Principal nth root. If a is a real number with at least one nth root, then the principal nth root of a is written as n over a, is the number with the same sign as a when raised to the nth power equals a. The index of the radical is n. So again, it sounds a little confusing, but we're going to look at this right now. So we're going to say simplifying nth roots. We're looking at the example, starting with a. So we're going to say 5 root negative 32. So then we're going to say, what is going to give us the 32s? Well, I would say we're going to start with negative 2. Yeah. Well, actually, you know what? Let's see what we can do here. So we can try and break it down and see how many, what goes into 32. Let's see how we can break this down. I'm just gonna, I mean, this is a simple one, but if we wanted to figure it out, there would be 5 portions of it. And so really the only thing that can be is 2, negative 2. Multiply it 5 times. 2 to the second power is 4. Third power is 16. 8. Wait a minute here. Sorry, my brain's not working. 2 squared is equal to 4. 2 to the third power 4 is going to be 2 times 2 times 2 is going to be 8. Okay, then 2 to the fourth power is 16. 2 to the fifth power is 32. There we go. Base 2. I kept trying to square the resulting number, but you don't. You simply continue it by the power of 2. Okay, good. Now, and the negative carries over, and that's because, yeah, if you go negative 2 to the fifth power, you're going to get negative 32. All right, and then all right, let's go to B. Four to the fourth power times 4 to the 10/24th power. Okay, 4 times 4 is 16, times 4 is 64, and I think it's 128. Wait a minute. Let's see here. 256. 4 times 4. Yeah, 56. 56 times, okay, except this is, we're doing, this isn't powers, this is square roots. 1096. So what we're going to do is we're going to combine the two. So this is what they want us to do. Hang on a minute here. 1024, not 1026. It would help if I wrote it correctly. So we can combine the two, and that's going to be 4 root of 4096. So let's try this. So if you want to get this result, we have to, so in other words, it's a number that's multiplied 4 times by itself, or we can square root it twice. So if it's like this, so 4 of the number is equal to square root of a. So that's essentially another way to think about it. Now, I could be wrong, and again, you have to be very careful with signs on this stuff, so be extremely careful with signs. But in this case, the answer is 8. So square rooting of 4096 gives us 64. Square rooting of 64, of course, is 8. All right. Now, let's go next. Okay, this stuff's getting complicated. Here we go. These are the examples we're looking at right now. So the bottom one is clearly 5. 5 times 5 is 25. Times 5 is 125. Okay, so, and then that's going to be 2, the top, because takes to the third power is 2, so we're going to say 2, and then that should be x squared. Squared over 5. And that should be, I think that's the answer. Let me see here. Negative 2x squared over 5. Yep. And again, whenever you have this kind, just take your take the radical and then take the power, and then we're gonna say like this: 3 over 6x, which is equal to x to 2. Actually, no, hang on a minute. Did I do that right? No. I did it wrong. I mean, I'm going to correct this. So that's going to be 6 divided by 3 x squared. And remember, when you do this, then this gets burned, right? There's no additional. That means you are taking a cube root of it. That means you're taking a number that's, instead of, think of it like a square root, you take a number by a number, but this is a number by a number by a number. And in the power, this x to 6 is 6 x's in a row. So that's how we get that. All right, and then D. Eight minus 2 4 root 3. Okay, well, let's see here. Our radicals are the same, therefore we could perform arithmetic on it. Okay, so yeah, that's fine. Okay, carrying on, we have using rational exponents. So yeah, this is the same as a1 over n. Okay, and then a to the m over n is equal to, the bottom one goes on the outside and the top one goes on the inside. Okay. So this is rational exponents, and you just have to, you have to kind of understand the way fractions work and so forth. But if you just remember the top example here, the 6 is the m, the 3 is the n. Okay, so right here. So, and that's just how you do it. The power on the inside, you can think of it this way, right? It exists in its own little world. If we were to just put it in its own little world and forget about everything else, it's just a variable to a power, right? It's just an exponent. And then the other part, so that part, we remember that would be the top, because it's still the power. And we know that the square root, it is a fraction, basically, a power to a fraction, which we apply to the bottom of it, and we combine the two. So just, that's a way of thinking about it. Sometimes you got to kind of like wire your brain in slightly different ways, come up with these little shorthands to kind of build a mental picture that works for you. And if it works for you, great. If you want some other mental picture, go for it. But just find a way to make it work for you. Okay, so we want to do 343 to the 2/3 as a radical. And we're going to simplify it. Okay, so then this is equal to, we're going to have to the 343 squared, and then we're going to divide it in 3. So, well, we want to simplify that. So, well, what can we do? Let's try to multiply for a second. 343, is that a number I'm familiar? Let's see here. Before I go any further, yeah, I'm going to square it. 11,7,649 and divided by the third. Yeah. Oh, I'm sorry. Wait, hold on. Right as a radical. This tells us that's the root. Now, let's see if they have a trick for simplifying this thing. We know that root 3. Okay, here we go. So the way we would try to solve it, we can make it really big, like 343 times 343 gives us 11,7,649, but that increases significantly the number of numbers we'd have to go through to try to guesstimate what it can be. Like we can start by taking a number, I don't know, let's say like 100, right? Times 100 times 100, and you can kind of bracket it, and that's going to be, let's see here, that's 1,000,000 basically. So, but there's another way. So if you look at 343, what 3 times itself is going to give us that number? Well, let's start with something smaller. Let's try 13. Well, 13 times 13 is 169. And so that wouldn't work. That's too big. Let's say 10 times 10 times 10 is 1,000. Too big. Let's try 8 times 8 times 8. If I have 12. All right. And let's try 6 times 6 times 6. 216. Maybe 7. 7 times 7 times 7. Perfect. Okay. So we know now we're going to cancel these two, and we're going to say this is 7. Okay. Now, when we cancel, this is now killed right here. We no longer have the square root, because this is a unit, right? This is the same thing as this is basically is equal to just this, right? So if we have that number on the outside, what they're saying is we want to cube root it. The circle one is the cube root, and then the other one's the square root, but we don't write the 2, we just write the radical sign. Now, just keep in mind that if you're used to just seeing the radical and just doing square rooting, and you see a 3, and it's you start trying to apply that operation, and then you're like, okay, and now I got a square root. No, it's a combined item. So that's just the way to think about it. So now that's gone. All that's left is 7 squared. 7 squared is equal to 49. All right, perfect. So yeah, the answer is 49. Cool. Okay. All right, and now we have rational exponents. All right, let's do this. We're going to say okay, rationalizing that. Well, let's see what they say. The power of 2 and the power of 7 will be 7, 2. Oh, okay. That's cool. Yeah, that makes a lot of sense. So 4 over a over 2/7. And if we... Oh, yeah. And then this is the same as writing 4 over a negative 2/7. So, for instance, this is the same as this. So if you want to take a power from the denominator to the numerator, then you just have to make it a negative, because the negative drops you down into the denominator on a power. Okay, so we have all right. A. Okay. Times to the 1/5. All right. Well, I'm guessing we're gonna do some just multiplying of the elements. I'm just gonna try to solve this. And let's see here. So if we have it, we're gonna say x is gonna be 3/4 times 1/5, which is gonna be equal to 5 times 6 times x 3/20, which is equal to 30 x 3/20. Let's see if I got this right or wrong. Okay, I got it wrong, but I was close. The difference is that it's addition. It's not multiplication. Just got to add them, because it's not power to a power. You have to add. That's right. I would have known this if it was like this. If it was like this, I know it's x to the 5th power. But if it's like this, that's going to be, you multiply this, that's x to the 6th power. See how that works? All right, let me fix that. But because it's in fraction form, it threw me off a little bit. So we have, so that's going to be equal to common denominator. So we're going to say 3/4 plus 1/5, which is equal to 5/5 times 3/4 plus 1/5 times 4/4. So that's going to be 15/20 plus 4/20, which is 19/20. So that's a 19 up there. And okay, 30, 19/20 of x. That's our answer right there. Okay, good. Now all of this is written out if you wanted to read it for yourself. But I'm trying not to look at the answer for this example. The examples aren't the ones that I'm really worried about. They're mostly the teaching tools. It's when we start doing section exercises, then I will try to solve them. Of course, we'll make mistakes. But when you check the back of the book, you try to correct them and move forward. The important thing is to understand the process. If you make a mistake, you have to understand where the mistake was and how to fix it. It's not bad that you made a mistake. It's bad if you don't understand something. Do you see that? It's one thing to make a mistake, but it's totally another to remain in ignorance. So that's what we want to avoid. We're trying to reduce the amount of ignorance by shining a light on everything that we can. All right, so here we go. Here we go. We're going to say 16/9 -1/2. So if it's a negative, we're going to flip it. Let's say 9/16 to the 1/2. Okay, and that's going to be 3/4. Yep. All right, that's right. Good. All right. Well, I'm going to end the stream here. And then next time, I expect that to be tomorrow, we will finish section 1.3 by going through all of the exercises that we've gotten. We've made our way through, what about? How many pages did we do? 3. We did 7 full pages. Or maybe, yeah, it was 7 pages. And now we are in page 39, which is a section exercises. So yeah, we're going to do 39 and 40 next time. And then we're going to go into polynomials, section 1.4. This is great. This is going to be so much fun. All right. I hope you enjoyed the stream. I know I did. Hope to see you next time. And thank you for stopping by.